video on determining the mole ratios. Mole ratio is the ratio of number of moles of any two substances in a balanced chemical equation. And the concept of mole ratio is very important in stoichiometry problems, because all stoichiometric calculations involving equations, they always use the mole ratios. So we need to learn how to determine the mole ratios from the balanced chemical equation. So how are the mole ratios derived? They are derived from the relationship between the coefficients of a balanced chemical equation. So these are the coefficients of a balanced equation. This equation is a balanced equation. This shows that for every 1 mole of nitrogen used, and for every 3 moles of hydrogen used, 2 moles of ammonia gas or 2 moles of ammonia molecules are produced. So if this equation is absolutely true, then we can make equivalents from here. So we are going to make the mole ratios as well. So first let's write down the equivalents. So here for every 1 mole of nitrogen consumed, 2 moles of ammonia is produced. So that is true from this equation, correct? So that's our equivalent. 1 mole of nitrogen consumed, 2 moles of ammonia is produced. And this truth is coming from this balanced equation. Similarly here, another truth. What is another truth from here? This equation is for every 3 moles of hydrogen consumed, 2 moles of ammonia are produced. So you see how these moles are showing the relationship between the products and the reactants. So I'm going to write here, for every 3 moles of hydrogen consumed, 2 moles of ammonia are produced. So this is another equivalent. What can be another equivalent here? This can be another equivalent. So for 1 mole of nitrogen consumed, 3 moles of hydrogen are consumed. So for every 1 mole of nitrogen consumed, 3 moles of hydrogen are consumed. So here, that's all. These are the only 3 equivalents that we can make from here. So from one equivalent, we can make 2 conversion factors. So we can write here 1 mole of nitrogen consumed, 2 moles of ammonia produced. Alright, and we can make another fraction, 2 moles of ammonia produced, 1 mole of nitrogen consumed. Similarly here, 3 moles of hydrogen consumed, 2 moles of ammonia are produced. And another fraction we can write from here is for every 2 moles of ammonia produced, 3 moles of hydrogen are consumed. Similarly here also we can make 2 fractions for mole ratios. So for 1 mole of nitrogen consumed, 3 moles of hydrogen is consumed. Or you can say for 3 moles of hydrogen consumed, 1 mole of nitrogen is consumed. Okay, so here if you have to write the ratio, nitrogen to ammonia, this is 1:2. Ratio for ammonia to nitrogen, it is 2:1. Ratio for hydrogen to ammonia, 3:1. So these are the mole ratios. For mole ratios, so this is for hydrogen to ammonia, it is 3:2. For ammonia to hydrogen, the ratio is 2:3. For nitrogen to hydrogen, the ratio is 1:3. For hydrogen to nitrogen, the ratio is 3:1. Okay guys, so that is the ratio here. I have this right here also. So where am I getting these numbers from? All these numbers in these fractions. Once again guys, all these mole ratios are actually the conversion factors. Okay, and I'm getting all these numbers from the coefficient of a balanced equation, all these numbers. So I don't want you to go back, but I want you to just look at this equation and fill these blanks without going back. Okay? Try yourself. Here comes another one. So here I already have written the equivalence. Let's see the relationship. So for 2 moles of hydrogen consumed, how many oxygen are consumed? 1 mole of oxygen. When no number here, it is 1. For 2 moles of hydrogen consumed, 2 moles of water are produced. For 1 mole of oxygen consumed, 2 moles of water are produced. Again, we can make 2 conversion factors from each equivalent. So for 2 moles of hydrogen consumed, 1 mole of oxygen is consumed. And another fraction you can make is 1 mole of oxygen consumed. For 1 mole of oxygen consumed, 2 moles of hydrogen are consumed. Okay. So if I'm going to come back to the ratio. Here again, for 2 moles of hydrogen consumed, 2 moles of water are produced. It's coming from the balanced equation, from here and from here. Okay. So I'm going to write here. So we can make 2 fractions from here similarly. Now I'm right, even though I'm switching the numerators and denominators, but they're conveying the same information. Once again here, so 1 mole of oxygen consumed produces 2 moles of water molecules. Or you can say that 2 moles of water molecules are produced when 1 mole of oxygen is consumed. Either way. When you have to write the ratio for this one, for hydrogen to oxygen, the ratio is 2 to 1. For oxygen to hydrogen, the ratio is 1 to 2. For hydrogen to water, the ratio is 2 to 2. For water to hydrogen, the mole ratio is 2 to 2. For oxygen to water, the mole ratio is 1 to 2. And for water to oxygen, the mole ratio is 2 to 1. Now here, I'm going to ask you to try this actually on your own. Here, how many mole ratios can be correctly obtained from this combustion of propane? So this is an equation showing combustion of propane, and propane is a hydrocarbon. When hydrocarbons burn, they produces carbon dioxide and water, and it's a combustion reaction. You can see you have elemental oxygen on the left side. So I want you to write the equivalents, as many equivalents you can write. Okay, so here each mole ratio, it relates to the number of moles of one reactant or product to the number of moles of another reactant or product. So here you go. So I have everything for you. I'm just going to explain this. So for 1 mole of propane consumed, 3 moles of carbon dioxide are produced. Okay, or you can say for 3 moles of carbon dioxide produced, 1 mole of propane is consumed. That is how we are getting this and this 2 fractions. Similarly here, for 1 mole of propane consumed, 4 moles of water are produced. So here 1 mole of propane consumed, 4 moles of water are produced. So the word produced is for the products, consumed is for the reactants. Alright, just remember, products produced, reactants consumed. Let me write it down here. These are the reactants and these are the products. Reactants are consumed during the reaction and products are produced. Okay. Now the next one is 3 moles of carbon dioxide. It's on the product side, so it is produced. And when 3 moles of carbon dioxide produced, 4 moles of water molecules are produced here. Or you can say other way, when 4 moles of water molecules are produced, 3 moles of carbon dioxide molecules are produced. This is a product side. So that's how you got 2 fractions, 2 mole ratios. Here the last one, not the last one, here 1 mole of propane. 1 mole of propane, it is a reactant, so it is consumed. It is also When it is consumed, same time the 5 moles of oxygen are consumed. Here again 2 fractions. Here is the next one. For 5 moles of oxygen consumed, because it's on the reactant side, 3 moles of carbon dioxide are produced. So 5 moles of, so here again 2 conversion factors. So 5 moles of oxygen consumed, we have 4 moles of water molecules produced. So again 2 conversion factors. So what's happening here? My question was, how many mole ratios can be correctly obtained in this reaction? So I gave you choices 1, 4, 12 or 16. So when you count these, the answer is going to be 12. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Alright. So here is the formula, guys. Number of mole ratios you can write for a chemical reactions are this one, n minus 1. So where n stands for the number of substances in a reaction, in an equation. So if there are 3 substances, then your n is 3. 3 minus 1, 2. It will be 6 mole ratios possible. Okay. When there are 4 substances, meaning n is 4. Your n is 4. So you have 4. And then n minus 1, meaning 3. So that means 12 mole ratios possible. Now when your n is 5, so n minus 1 here 4, you have 20 mole ratios possible. Okay. I hope guys the video was helpful. You can go back anytime, pause it, watch it again. And thank you so much for watching.